All right, thank you all. It's really my pleasure to be here, and thank you for having me. Thank you for inviting me to begin this morning. It's a pleasure. Oh, that's my thanks. My talk is like Bob said. I'm going to be giving 3 talks called 85 Years of Nielsen Theory, and the basic idea is this is just a general overview of the major themes and threads of Nielsen theory over the many years. So my audience is really not necessarily for the experts in the room, which unfortunately for me is most of you. My audience, I think, is for students and other people who are not necessarily the global leaders of Nielsen theory. Unfortunately for me, this audience probably, well, I'm sure that most of you know more about what I'm going to say than I do. So I would appreciate any comments. Feel free to ask questions or voice objections. I hope I haven't left anything out that you feel is really important and I'm skipping. Please feel free to interrupt and ask me questions. I hope that you can you all hear me? Yes? All right. Everyone who's listening to me can hear me. Okay. And in case you can't hear me, I'm going to record the screen of my presentations and put them on YouTube. So tell all your friends. This will quickly be the least watched video series on YouTube, I think. Okay, so I thought I'd start off by just talking about a few. There have been a few books about Nielsen theory. These are kind of the principal references. The first one is Bob Brown, Leftshuts fixed point theorem.
You made your first mistake. The date is wrong.
It is?
Yeah, I think it's
71.
71. Yeah.
Okay. Sorry. All right. I hope that's my only mistake. Yes, it's kind of hard to find this book these days, but it still works. The next major one, Boju Jiang from 1981. Is that correct? All right. There was also a book by Jiang in 1989. Is that? All right. I'm not going to ask every time. This one is at a, I would say, a more elementary level than the Jiang book. It's, I think, suitable for strong undergraduates. It's a good introduction to the basic ideas. And then a recent one by Yezierski and Marzantovich, Homotopy Methods in Topological Fixed and Periodic Points Theory. This, Oh, with I. Sorry. Right here. Should be an I. Sorry.
Second mistake.
Yes, okay. Maybe I shouldn't have said. You can feel free to. All right. Yeah, this one includes, as far as I can tell, it includes almost all of the material in the Jiang book, plus some more recent things, with a lot devoted to the periodic points theory, which is only a little bit in Jiang's book. And this is not difficult. All the other ones are out of print. This one is not, so you can get it pretty easily. All right, let's begin. So I'm going to start longer than 85 years ago with the Brouwer fixed point theorem, which was published in 1912, but I think there's evidence that people were talking about it before then. So it says any self-map of the disk has a fixed point. That's a point x with f of x equal x. What about spaces other than the disk? It's a nice theorem, the Brouwer fixed point theorem, but the disk is pretty restrictive, I suppose. A more general result was obtained by Leftshuts for any self-map of a compact polyhedra. Now, the results actually throughout the talk today are usually can be a little more general than polyhedra, but I'm just going to focus on compact polyhedra and sometimes just manifolds. Anyway, Leftshuts defined the Leftshuts number as this. It's the alternating sum of the traces of the maps in the homology. This is a homotopy invariant because of it's using the induced maps on homology, and it turns out it's always an integer, even if you use the rational coefficients in the homology. It turns out you will always get an integer when you do this Leftshuts number, the trace. So about 85 years ago was the Leftshuts fixed point theorem. By the way, most of the early history I'm using Bob Brown's article in the History of Topology volume as a reference for the the history. It seems to me that a lot of these, around this time, around 85 years ago, there were several different people coming to similar realizations around the same time, and it's difficult for me, at least, to tell exactly who is responsible for what. Anyway, Bob has a great article about this. So the Leftshuts fixed point theorem says if that number, the Leftshuts number, is non-zero, then f has a fixed point. So Leftshuts gave his proof for compact manifolds. Hopf, a few years later, did it for Polyhedra. So if the space is the disk, then it's easy enough to compute this trace in the homology. If you have the disk, then the homology groups are all trivial except for the bottom one. So all of the traces will be 0 except for the lowest dimension, which is the map is the identity, so the trace is 1. So the Leftshuts number is 1 on the disk, which means there's a fixed point, and so you get Brouwer's fixed point theorem for free if you have the Leftshuts. That's why I said the Leftshuts theorem is a little bit more general. Let's talk a little bit about the Leftshuts number. Why should you use this trace? Why does it have anything to do with fixed points? Let's first of all talk about a simplicial map on a compact polyhedron. And let's assume the Leftshuts number is non-zero, and I'm going to try to explain why there has to be a fixed point. If the Leftshuts number is non-zero, then one of those traces, when you added up the traces, one of the traces must be non-zero. And so that means there's some simplex in that dimension, say dimension q, which goes to itself. That's what the trace is, right? But I should say here, I suppose it's not just s, maybe a constant times s. Could be minus s, could be something else. Anyway, since s, though, is topologically a disk because it's a simplex, that means by the Brouwer fixed point theorem, there will be a fixed point in that simplex. And so the map has a fixed point. More or less, this is good enough to prove the Leftshuts fixed point theorem for simplicial maps. If your map is not simplicial, then you can change it by homotopy to be simplicial by the simplicial approximation. And since the Leftshuts number is homotopy invariant, then that's good enough for non-simplicial maps. I just want to talk a little bit about why the alternating sign in the Leftshuts number. What I just said, actually, you don't need this part, the alternating sign. Everything that I just said would still be true even if that was missing. I was being a little sneaky, though. I was talking about simplices. I said S is a simplex rather than homology classes, which is really what you should talk about in the trace of homologies. So actually what I just said would be a valid argument for the trace of the chain maps, right? Not the homology maps, but the chain maps. But there's a theorem by Hopf that says this trace with the alternating sum of the chain maps is equal to the trace with the alternating sum in the homology. That's called the Hopf trace theorem. And that's why you need the alternating sign. The Hopf trace theorem is true because of the alternation of the sign. So if you leave out the sign there, then you wouldn't have a well-defined invariant in the homology. It would work in the chains, but not in the homology. All right. So we should think of the Leftshuts number like a homotopy invariant algebraic count of the fixed points of f. By that I mean it's like you're counting the points with multiplicity. So it's not actually a perfect count of the actual number of fixed points. That's because, for instance, it's possible to have the Leftshuts number be 2 with only one fixed point, which is like a double fixed point. And also it's possible to have, say, the Leftshuts number be 0, even though there are 2 fixed points with kind of opposite signs that can kind of cancel each other out in the sum of the traces. So that's what I meant when I said the Leftshuts number is not a perfect count of the actual number of fixed points. Generally, the converse of the Leftshuts fixed point theorem is not true. That is, if the Leftshuts number is 0, that does not mean there are no fixed points. It's just there could be fixed points with have kind of alternating or opposite signs. And this business, what I'm saying about the signs, you can actually formalize this. The Leftshuts number can be localized into a specific integer kind of multiplicity for each individual fixed point, if the fixed points are isolated. And this localization is called the fixed point index. So I want to talk a little bit about that. In dimension 1, it's easy enough to do the fixed point index. So in dimension 1, in any dimension. The fixed points are intersections of the graph of the function with the diagonal submanifold. Here's a picture. I hope you don't mind my hand-drawn pictures. I didn't have enough time to make all the pictures in the computer. I like the hand-drawn. So this is the kind of picture in dimension 1. This is actually what it will look like. And the fixed points are the intersections with the diagonal line there. There, I circled them. Sorry if you can't see that very well. There are 3 fixed points in this picture. And the fixed point index is going to be defined in such a way that that one on the bottom is a -1, the one in the middle is a +1, and the one up there is a 0. And it has to do with the way that the graph crosses the diagonal line. All right. The index depends on the slope as f passes through the diagonal. And you can be specific about this. So when this thing is non-zero, the index is the sine of 1 minus the slope, right? So when the slope was equal to 1, which is the case in the last one there, it was 0. And in the other cases, if the slope is greater than 1, you get a -1 index. If it's less than 1, you get a +1 index. So it turns out you can do a similar thing in higher dimensions. So it's very simple in dimension 1. In higher dimensions, if f is differentiable and it has isolated fixed points such that the intersections of the fixed points in the diagonal are transverse, meaning they have kind of a generic sort of intersection, not a tangential intersection or anything strange like that, then you can define the index in this way: the sine of the determinant of the identity matrix minus the derivative matrix, the derivative map, the linear map, where I is the identity matrix. All right, and you can see how this generalizes the dimension 1 case. There's also a more general definition using homology and cohomology that gets to the index without using without the assumption that the map is smooth or that the fixed points be isolated and transverse. I don't want to get into that too much. And also axiomatic definitions exist, and they have for quite a long time. It's been realized that the Leftshuts number and the index also can be described by a few fairly natural properties, and then you can prove that they are the unique invariants which satisfy these properties. And those are good for definitions also. All right. So when x is an isolated fixed point, it happens that the index will add up and give you the Leftshuts number. So what I just said. Yeah, if you sum up all the indices of the fixed points, then what you get is the Leftshuts number. This is called the Leftshuts-Hopf theorem. It was proved by Hopf in 1929. And so this is what I meant. I said that the index is supposed to be a localization of the Leftshuts number. If that's true, then something like this should be the case. You should expect, if you add them all up, then you get the global Leftshuts number. All right? The index sums up to the Leftshuts number, and the Leftshuts number is a homotopy invariant, so we should ask, what about the index itself? If you change the map by a homotopy, how does the homotopy affect the fixed point index? All right? Well, one thing to notice is if you change the function by a slight homotopy, then the fixed points will move around slightly. All right? And in that case, the index, the fixed point index, will be preserved. Here's a little picture here. So if this is your map, you can see I have 3 fixed points. One is a +1, a -1, and a +1. If you move the graph a little bit, you'll see those 3 fixed points will move a little bit, but the indices will be the same because the crossing is still in the same direction if you only change it a little bit. What happens if you change it a lot? Well, let's take the second bump there on the graph and just kind of pull it down a little bit. You can see at some point there will be only one fixed point. Those 2 fixed points will combine with each other, and the resulting fixed point will be a 0 index. And you could continue to pull this thing off, and the fixed point would go away entirely, right? So what happens to the index when fixed points combine with each other? The index adds. This is the additivity property for the fixed point index, which is one of the basic properties of the fixed point index. All right. So the fixed point index of a set of fixed points is the sum of the fixed point index of a set of fixed points will be preserved by homotopies. All right. This raises an interesting question. When can you combine 2 fixed points by a homotopy? In dimension 1, I mean, in a picture like this, you could always combine any fixed points that you like. But more generally, when can you do that? Actually, this is a big question and is kind of the big question for Nielsen theory. So this is what we're going to talk a lot more about. All right, let's talk about, so it's related to the actual number of fixed points, not the Leftshuts number, like I said, is an oriented count of the fixed point. Let's talk about the actual number, specifically how many fixed points can be achieved by changing the map by homotopy. Can you change it to increase the number of fixed points? Can you change it to decrease the number of fixed points? One of those questions is very easy. You can always change the function to increase the number of fixed points. Here's a little picture. If I start with this has 2 fixed points. I can change the map by homotopy like that, which now has a lot of fixed points. Okay, and you can always, this is a dimension 1, but you can do the same kind of a thing. In fact, you can, instead of making that all wiggly over here, you could just make it go straight and you would have infinitely many fixed points right there. So increasing the, if you ask, what is the maximum number of fixed points that you can achieve? That's not a very interesting question. The answer is always infinity. What about the minimum number of fixed points that you can achieve? That is an interesting question. This is the definition. I'm going to use this notation for the minimal number of fixed points. It's the minimum possible number of fixed points of any map that is homotopic to F. All right? And this is really the central kind of thing that we study in Nielsen theory. Or that's what Nielsen theory was designed in order to try to compute this number. Much harder than maximum number of fixed points. And here's Nielsen's basic idea. So he did this first for homeomorphisms of tori, and then for homeomorphisms of surfaces in 1927, about 85 years ago. Group the fixed points into classes. That's the basic idea of Nielsen's approach. And the classes of fixed points are meant to group those fixed points which can be combined by homotopies. So in general, when you ask, which of these points can I combine by homotopies? The answer is some of them you can combine with each other, and some of them you can combine with each other, but there are some that you can't combine with each other. And the fixed point classes are meant to capture this idea of which fixed points can you combine with one another. And the minimal number, or the number of such classes, will be a lower bound for the minimum number of fixed points. In the best case, you could imagine combining all the points from each class together. But since you can't combine points from different classes together, then the number of classes will be a lower bound for the minimum number of fixed points. All right. So the basic theory is from Nielsen. And a lot of work was to formalize and give some basic properties was more or less immediately done right after by Meister and Wecken. So here's the idea behind the fixed point classes. We're going to look at the covering space, the universal covering space, and P is the projection. And we're going to consider the fixed point sets of the liftings of F. So F has certain fixed points. And when you consider the lifts of F, they also have fixed point sets. We're going to choose a specific reference lift called F tilde, and then all the other lifts look like some covering transformation times the chosen reference lift. So this gamma is an element of the fundamental group we're going to consider as a covering transformation on the universal cover space. And it's pretty easy to show that any fixed point, the set of fixed points in the map downstairs can be sort of decomposed into a union of fixed point sets of the lifts. All right? And those sets in the union on the right-hand side there, those are the fixed point classes. All right? This is Nielsen's approach to the fixed point classes. So we could say informally, 2 fixed points are in the same fixed point class. They're called Nielsen classes when they both come from fixed points of the same lift, right? And Nielsen saw that this is a necessary condition for fixed points to be combined by a homotopy. If you want 2 fixed points to be joined by a homotopy, they must both come from fixed points of the same lifting of the map, all right? There's actually another more kind of cuter geometric definition that Nielsen also came up with. 2 fixed points are in the same Nielsen class if and only if there's a path alpha from x to y, such that alpha is homotopic to f of alpha as paths with fixed endpoints. Here's a picture of that. So x and y are both fixed points. You take a path from x to y. Since x and y are fixed points, when you do the map, when you do f of alpha, it will again be a path from x to y. And the condition is that those 2 paths be homatopic as paths. If that is true, if there exists such an alpha, then x and y are in the same Nielsen class. This is equivalent to what I just said about the covering spaces. All right. This one is nice because it's pretty clear in this picture that this is a necessary condition for x and y to be combined by a homotopy. If you're going to actually combine those 2 points by a homotopy, it must be the case that there is a path like this, because when you join those 2 points, they'll travel along a path, and that path must satisfy this condition here, that f of the path will be homotopy to the original path. All right. It turns out, so this is a nice definition, but the one with the covering spaces tends to be a little more useful, easier to work with. All right. So this is what we're going to look at. The union on the right side is not actually disjoint. It's possible for some of these things to have intersections, but actually it's not too hard to decide when they intersect. So here's the condition. We say that gamma and sigma are in the same Reidemeister class. So this is sometimes called a twisted conjugacy class, when there exists another element in the group that satisfies this condition over here. So this over here looks like ordinary conjugacy of group elements, except for this part right here, this f. This is the induced map by the function that we're talking about. All right, this is called the twisted conjugacy classes. This is a generalization of the ordinary conjugacy relation. All right. And it turns out, so in this case we're going to write the class of gamma is the class of sigma. The brackets mean Reidemeister class. All right? And it's not too hard to prove that in this union here, 2 of the sets on the right, I said they're not always disjoint. It turns out if the 2 liftings that you're talking about are of the same Reidemeister class, then the 2 fixed point sets are the same. And if they're not the same class, then they're disjoint. All right? So this union over here, the Nielsen classes are more or less in correspondence with the Reidemeister classes, all right? Because the union up there is not disjoint, but it is disjoint if you only consider different twisted conjugacy classes, all right? Actually, some of the sets in the some of these fixed point sets of the lifts might be empty sets, and so really it's not an exact correspondence. We have an inclusion. I mentioned this actually because I was talking with Phil Heath last night. He said, "Are you going to tell them about the inclusion of the fixed point class in the Reidemeister classes?" I said, "This is it." So in Phil's talk, at one point he is going to say, "The usual inclusion." This is what he's talking about. All right. That's just for you, Phil. All right. Actually, the idea of twisted conjugacy in groups is as a purely algebraic question. This is something that people are studying a lot, even outside of Nielsen theory. People just in pure group theory. So the typical question is this: if you have a particular homomorphism of the group, endomorphism, or you can concentrate just on automorphisms if you want, and you have 2 group elements, then can you decide whether they are in the same twisted conjugacy class? All right. This is called the twisted conjugacy problem. It's the classical conjugacy problem for groups. This is a more difficult version of that. Here's another thing that you could talk about. I'm going to call this R of f is the set of Reidemeister classes, the set of twisted conjugacy classes. For particular maps, is this set finite or infinite? Or you could ask, are there groups for which this set is always infinite? You could specify just to automorphisms if you want. This is called the R infinity property of a group. So a group has the R infinity property, means the set of twisted conjugacy classes is infinite whenever the map is an automorphism. And there are lots of people who are working on this now. So people at this, in the next few days, Nasibulov, Felschen, and J.B. Lee are going to be talking about the R infinity property. It's a big deal these days. A lot of these questions here become easier if you assume that the map is an automorphism, like I said. I hope you don't mind, by the way. I'm going to try to mention when there are other talks that are related to things that I'm saying. And again, I hope I don't leave anybody out. You can interrupt me if I forget about you. Let's talk about the minimum number. All right. Like I said before, the smallest possible number of fixed points would be achieved if you can reduce every fixed point class so that it has only 1 point in it. Actually, that's not entirely true. Sometimes you can remove all the points entirely. So the minimum number would be achieved when every fixed point class has been reduced to a single point or has been eliminated entirely by homotopy. So let's talk about how do you know if a class can be totally removed by a homotopy? You can use the fixed point index, right? That's because if the index is not 0, then you cannot remove all the fixed points by a homotopy because the index is preserved by a homotopy, and it would be 0 if your set became the empty set. So for this reason, we call a Nielsen class is essential. That means its total fixed point index sum is non-zero. Right? And these are the ones which cannot be made empty by a homotopy. Like I said, if you actually made it empty, then the index would become 0, but the index is supposed to be a homotopy invariant. The number of essential fixed point classes, that's called the Nielsen number. All right? And we write n of f. And it's automatically true because of what I said before. The Nielsen number is a lower bound on the minimum number of fixed points. All right? Let's talk about some simple examples. So self-maps on the circle. The circle is the simplest compact manifold. Since the Nielsen number is a homotopy invariant, the only thing we care about really is the degree of the map, because we're talking about a circle here. And it's not too hard to see that any degree D map can be changed by a homotopy to f of z equals z to the d. I'm using the complex circle as complex numbers. And such a map has the absolute value 1 minus d fixed points. This is all simple. You can work this out. You can show, again, just by using the slopes of the graph intersections, you can show that these fixed points will all have the same index. They'll all either be +1 or they'll all be -1, depending if the degree of the map is positive or negative. And so, in that case, the Leftshuts number, if you add them all up, right, since there's 1 minus d fixed points and they all have index +or -1, the Leftshuts number will be +or -1 minus d. That's easy enough. What about the Meister classes? If we want to know the Nielsen number, you have to know how many fixed point classes there are. In the circle, the fundamental group is the integers. So when are two integers twisted conjugate? You've got to solve the twisted conjugacy problem in the integers. It's not hard, though. So just the definition of the twisted conjugacy means there's some z. I'm writing the group operation as addition here because the integers is a billion. All right, this is the twisted conjugacy relation. Can we sort of figure this out? Yes, we can. If the map is degree d, then f is multiplication by d. Combine the z parts there, and you can see. So x and y are twisted conjugate if and only if x is equal to y mod 1 minus d. You can see they differ by a multiple of 1 minus d. All right. So the Meister class, the set of Meister classes, you can consider as the same as the integers modulo the absolute value 1 minus d. All right. And remember, we had 1 minus d fixed points of the same index, and it's actually not too hard using the covering spaces to show that they all have different Meister classes. So what does that mean? We had that many fixed points. They are all in different classes, and we also said they all have index +or -1. So they're all essential classes, and so the Nielsen number is actually equal to that number, the absolute value 1 minus d. In fact, that's also the minimum number of fixed points. The Nielsen number is a lower bound on the minimum number, and we already said that that map in particular already has that number of fixed points. So in that case, the Nielsen number and the minimum number are the same. So the Nielsen theory of the circle is pretty easy. Once you know the degree, there's formulas for everything that you want to know. What about tori? Tori is not much harder, actually. Anyone know who this is? Is the picture? Probably not. This is if you search on Google for Nielsen theory tori, you are likely to come across this woman. This is an American woman. Her name is Tori Nielsen. Tori is a common first name for women. There's actually several people named Tori Nielsen. This is what you get. Anyway, I don't know her. I'm sure she doesn't mind. Okay, so on tori, there's a similar formula to these simple formulas on the circle by Brooks, Brown, Pak, and Taylor, 1975. So you can view the torus as the quotient of Rn modulo the integer lattice. And then a map on the torus, you can always change by homotopy to sort of linearize into an n by n matrix with integer entries. And then they showed that such a map has this many fixed points. The absolute value of the determinant of I minus AI is the identity matrix. All right. This should remind you of absolute value 1 minus d. Right. This is a higher dimensional version of that. Furthermore, all of the other things that I said before are also true in this case. They're all in different, all those fixed points are in different fixed point classes, and they all have the same index, either +1 or -1. And so on tori, we have this formula for the Leftshuts number, and the Nielsen number is the absolute value determinant identity minus A. All right. So again, the Nielsen theory on tori is pretty straightforward. I mean, at least you can work it out into nice formulas. It turns out some similar things are also possible on nil manifolds, which are more general. A nil manifold is a quotient of a nilpotent Lie group by a discrete lattice, so that you get a so that the result is a compact manifold. In these, so a torus is an example. Torus being Rn modulo the Zn, but more generally, you can do similar tricks with the Nielsen theory of any nil manifold and get similar kinds of formulas and similar sort of ideas of linearizations. All right. So yeah, tori are nil manifolds. That's what I just said. And this is also what I just said. On the nil manifolds, you can similarly linearize the maps, and you can get nice formulas. This was done sort of independently by Anasov and Fadel Husseini in the 80s. All right. Actually, the results on nil manifolds and solved manifolds also, you can do similar kinds of things for solved manifolds. They use some general properties for Nielsen theory on fibrations. If you have a fibration like this, where F is the fiber and B is the base, and a fiber map, which looks like that, then this is something that Bob Brown, I believe, was the first to look at. The question that is in that Bob raised and tried to address was, when can you have a product formula like this? The Nielsen number of the fiber map is the product of the map on the fiber and the map on the base. And this, if your fibration is a product, an actual Cartesian product, like a trivial fibration, then this this came to be called the naive product formula. And this was known for a long time to be true of the Leftshuts number and the fixed point index. Knowing that it's true for the fixed point index is not too hard to show that it's also true for the Nielsen number. So the question was, when can we get the product formula for fibrations? It's not always true for general fibrations. There are some conditions. So this is something that people kind of wrestled with for a while, but by 1981 it was settled. You gave some necessary and sufficient conditions for the product, the naive product formula to hold for fibrations. I don't really want to get into the details, but if this is something you're interested in, there's plenty of work on this. I will say specifically, fibrations over tori behave very nicely, and there are nice kind of torus fibrations for nil manifolds that make all of that stuff work. And you can see Phil's talk for some more on fiber methods. He'll probably say fiber that way. But that's American spelling. All right. So here's a major theme in Nielsen theory. Choose some category of spaces and self-maps and try to compute the Nielsen number. Right? I've talked about circles, tori, fiber spaces. Actually, those are all fiber spaces. They're all products. Surfaces have been a major topic over the years, and Evelyn Hart is going to give several talks about that. Dassenberg, I said later today. Is he going to be here? Yeah? Okay. He will be very tired, probably. But yeah, he's going to talk about some results on surfaces also. Something that's fairly new, that the geometrization theorem, now that it's been proved, you can there's some sort of new ideas for three manifolds that you can classify three manifolds according to their geometries and try to get somewhere based on that. Peter Wong is going to talk later today about that. Typically in these scenarios, at least in the best case, a method for computing is successful when the Nielsen number can be reduced to calculations of the Leftshuts number or to algebraic calculations involving the Reidemeister classes. In that case, you sort of feel like you've done a good job because you've reduced the Nielsen number, which is sort of a geometrical question, to these more algebraic questions. In many cases, the Nielsen number can be reduced to the Leftshuts number itself, and the Reidemeister number, that R of F, is just the number of Reidemeister classes. A lot of times the Nielsen number only depends on those two, and those are reckoned to be really good situations. That means the Nielsen number can be computed entirely algebraically. Yeah, that's the Reidemeister number, that last quantity there. This is actually true for a large class of spaces called the Jiang spaces. This may be the first time I've mentioned Jiang. This is certainly not the last time, though. So the Jiang spaces, it's a large class of spaces for which Jiang proved that the Nielsen number can be computed purely in terms of the Leftshuts and the Reidemeister numbers. This includes Lie groups, actually topological groups, which is more general, actually H spaces, which is more general, generalized lens spaces, simply connected spaces, quotients of Lie groups by finite subgroups. I believe that was Peter. Unfortunately, the Jiang spaces, the classical Jiang spaces, all have abelian fundamental groups. That's a necessary condition to be a Jiang space, which is fairly restrictive. But there are some other spaces which we call weakly Jiang, which means when the Leftshuts number is 0, the Nielsen number is automatically 0, and otherwise the Nielsen number is equal to the Reidemeister number. So this is what I was saying by the Nielsen number is entirely computable in terms of the Leftshuts and the Reidemeister. All right. This is true for Jiang spaces, and this is the definition of weakly Jiang is a space for which this is true. In these cases, the geometry of the fixed point set is very closely tied to the algebra, right? That's what I was saying before. And for some spaces, this sort of a relationship is known to be impossible. That is, sometimes the Nielsen number cannot be computed just in terms of the Leftshuts and the Reidemeister number. An example, this is why the R-infinity property is of interest, at least one reason. Any space where the fundamental group has the R-infinity property cannot be a weakly Jiang space. In that sense, the R-infinity property, is that true? He says yes, he says no. Hi, sorry to interrupt myself. What I just said right there is not exactly true, and thanks to Peter Wong for pointing this out. I was trying to refer to a general slogan that you see in the papers about the R-infinity property. They usually say something a little less formal than what I said. What I said was a little too formal. Anyway, what they usually say is something like, any space with the R-infinity property for the fundamental group cannot have a Jiang sort of result for the Nielsen numbers. And what they mean by that is, specifically, the Nielsen number for such a space cannot be reduced to the computation of the Reidemeister number. And that's just obviously because on an R-infinity space, the Reidemeister number for a homeomorphism will always be infinite. And so it's not possible that the Nielsen number could always equal the Reidemeister number, because the Nielsen number is known to always be finite. So what I should have said is something a little bit more vague, not that any space with the R-infinity property cannot be a Jiang type space, but just that a space with the R-infinity property, you could say the fixed point theory cannot be determined completely by the Reidemeister theory. So for those spaces, the Reidemeister theory is not adequate to completely explain the Nielsen theory. All right. Sorry about that. Back to the show. Okay, so we talked about the Leftshuts number, 1926, the Nielsen number, 27, and the fixed point index and the Leftshuts-Hopf theorem. So this is the beginning of what I call the 85 years of Nielsen theory. The two in...
You mentioned 1913, 100 years.
Yeah, well, that's Brouwer. I decided that doesn't count as Nielsen theory.
No, you mentioned Nielsen result.
Oh, that's true. Yeah. Yeah, that was...
Nielsen actually got his PhD in 1912.
Uh-huh,
For the
okay.
Nielsen number, for the Nielsen theory of the throws.
Yeah, that's only
But
for
I mean,
the
but that was
torus.
so special. I think 27 was when he got 300 pages of nothing. Anyhow, a very fancy journal to do this.
Right.
So that's really, I think 27 is a good year.
Thanks. Okay, I need a break. Okay, so the two invariants, the Leftshuts and the Nielsen number, were combined in a clever way by Reidemeister and Becken. The idea is, let's do this is the Leftshuts number, the trace in the homology. You're going to do the same thing, only we're going to do it in the covering space, the universal covering space, instead of the space X itself. All right. So the universal cover, if you want to talk about the chain groups, it has the same kind of simplicial structure as the base space, but for every simplex in the base space, you get infinitely many copies of it, and the copies are parameterized by the deck transformations, the covering transformations. All right. So you can consider the universal cover space is basically the same as the base space, the chains, but instead of integer coefficients, you allow integers with covering transformations as coefficients. All right. So z pi coefficients. That's the group ring instead of z. And then you can write your map, the lifting map, as a matrix. Now downstairs, you write the map as a matrix with integer entries. Upstairs, because the simplices have these z pi coefficients, you can write the map as a matrix with z pi entries. And then you can do the trace as usual, and you will get a z pi element. All right? So this is now called the Meister trace, and it is, like I said, it's the same as the Leftshuts number, but you do it in the covering space. And instead of getting integer, you get a z pi element, an element of the group ring. This is the Meister trace, sometimes called the generalized Leftshuts number also, because it's like the Leftshuts number, but you do it on the covering space. I didn't mention this row here, which is around the whole thing. This is it changes the group elements into Meister classes. So the row just sort of combines all of the group elements by their twisted conjugacy classes. All right. This is the Meister trace. So this is a made-up example, and I'm not even telling you what the example is, but the Meister trace, it doesn't look like an integer. It looks something like this. You have integer coefficients in front of Meister classes. So in some imagined example, you could have a Meister trace that looks like this. What this would mean, that indicates that the map has a fixed point class with Meister class gamma, and that one has index 2, because the 2 is the coefficient there. There's a fixed point class with Meister class sigma, and that one has index -3. And then there's a fixed point class with class E, which has index sum 1. That's how you read the Meister trace up there. It tells you what the fixed point classes are, and it tells you what each of their indices are. And all of the other fixed point classes, all the other Meister classes have index 0. All right. So you can tell immediately from the Meister trace, the Leftshuts number is the sum of all the indexes, which would be the 2 minus 3 plus 1, that's 0. And the Nielsen number will be 3, because there are 3 classes here which have non-zero index. All right. So in general, the sum of the coefficients in, this should be RT, the Meister trace. The sum of the coefficients of the Meister trace is the Leftshuts number, and the number of non-zero terms is the Nielsen number. It's a nice little thing.
You're assuming that these are 3 distinct Meister classes.
Yeah, right. So when I wrote the brackets here, I mean, that's the class, and they're not the same class. Right, yeah. Yeah, thanks. The fact that the Meister trace itself is a trace makes this actually easily computable sometimes. That is, except for what she just said, deciding what the classes are. That turns out to be the hard part if you're using the Meister trace. All right. Okay, let's talk about the Nielsen number and the minimum number. This is kind of the last thing that I want to talk about today. So when are these two things equal? The Nielsen number is the lower bound for the minimum number, but I haven't talked about are they actually equal. So Nielsen's original setting was surface homeomorphisms, and in that setting it's not clear if they are always equal, although I assume that Nielsen believed that they were equal, because that's the whole point of the Nielsen number, is that it's supposed to be a measurement for this minimal number. At least he hoped that they were equal, I assume. So Vecken actually showed that they are equal when the dimension is not 2, which is everything that Nielsen was not talking about. If the dimension is 1, it's easy enough to show that, actually I think I already explained that they're equal. Yeah, when the dimension is 1, then it's just the circle and everything works out easily. When the dimension is higher, you can use some tricks. So this is called the Vecken theorem, that the Nielsen number is equal to the minimum number when the dimension is not 2. So, like I said, the dimension 1 is easy. In the higher dimensions, you know, the idea is you're changing the graph of the map and trying to move the graph away from the diagonal. And if the dimension is high enough, specifically you need 3 or higher, then there's enough room to move the graph so that it intersects the diagonal 1 time for each essential class, and you can move it all the way off when the class is not essential. I don't want to get into the details, but this is the basic idea. What about for Polyhedra? What I just said was just about manifolds. What about Polyhedra? So she, in 66, showed that the Nielsen number and the minimum number are the same for polyhedra with dimension greater than or equal to 3, and no local separating points. That would be a point for which if a neighborhood of that point is connected, but when you delete that point, it becomes disconnected. So if there are no local separating points, then it's true even for complexes. And then Jiang proved even for polyhedron in dimension 2, it is true as long as it's not a surface, which again is the only thing that Nielsen considered. The Nielsen number and the minimum number are the same for any polyhedron without local separating points, which is not a surface. What about surfaces? This was an open question for a long time. You can see already 1979 is a long time after Nielsen's original work. The Veckan issue for surfaces was also resolved by Jiang in the early 80s. Until this time, there was no example known with the Nielsen number different from the minimum number on a surface, but Jiang actually did construct such an example. So his example has a Nielsen number 0, but the minimum number is 2. In this case, there are 2 fixed points with opposite indices, but Jiang shows actually that you can't combine them by a homotopy. Or actually, if you do combine them, then suddenly 2 other fixed points will appear somewhere else. You can never actually completely remove the fixed point class. All right? Yes, so the class is not essential because they have different indexes. They have the total index is 0, but actually Jiang showed that you cannot remove both points at the same time. The paper is called Fixed Points and Braids. I want to just give you a very vague idea of what braids has to do with it. There was paper in 2 parts. Here's a very vague idea. Again, I'm not really an expert in this, but I'm not really going to say much either. So hopefully, I'm not going to say anything wrong. If you have, let's consider a map with 2 fixed points, such as Jiang's example is like this, and we're going to change the map by a homotopy and see what happens to the fixed points as we change the map. So let's use the pants surface, which is Jiang's example space, and the homotopy itself will be a map on the surface times the interval. All right. So I'm going to draw. Here's my surface times the interval. We're going to imagine the top part is sort of the original map, and then as you go down, you change the map by a homotopy until you get something else on the bottom. If we have 2 fixed points at the top, and we change the map by a homotopy, it might look something like that. All right? The 2 fixed points will dance around during the homotopy, and they'll end up somewhere on the bottom. All right? And this kind of thing is a braid. Right? This is called a 2-strand braid on the surface P. And there's a whole algebraic theory of braids on surfaces. It's a little more complicated than the classical braids. All right? There's an algebraic theory for surface braids. There's something called the surface braid groups. They're just like the ordinary braid groups. They have similar, there's a presentation with relators, like the braid relations. Plus, there's some other relators which have to do with the topology of the surface that you're talking about. You can see here those empty, deleted cylinders there will involve some extra. They'll cause some extra relations in the braid group that you get from this sort of a thing. Anyway, in Jiang's example, he shows that if you were to remove the 2 fixed points at the same time, this would force some sort of algebraic formula in the surface braid group to hold. And then he proves using the algebra in the braid group that actually such a formula is impossible using the braid relations. All right, that's the basic idea. And I hope I didn't say enough to say anything wrong. It's very vague, I know. And braid groups are playing a big role now in Nielsen theory. So I think the next talk actually will say something about braids. It's in the title at least. Jiang. So in the second paper, Jiang showed that his example on the pants can actually be embedded to make a non-Veckan map, that is a map with Nielsen number different from the minimum number in any surface of negative Euler characteristic. So it's not just for that particular surface. Pretty soon after, people asked whether the Nielsen number can be arbitrarily different from the minimum number, right? So we know the Nielsen number can be strictly less than the minimum number. Can it actually be like very much less than, or do they always have to be close? Actually, Mike Kelly showed that the difference can indeed be arbitrarily large. It can be as big as you want. There are examples for which the difference is very big. You could ask some related questions. If you sort of choose a map on a surface at random. You have to make some sense of what you mean by that. Is it likely that the two numbers are equal? Another way of phrasing this vaguely would be to say, are Jiang's type of examples the expected behavior, the ordinary behavior, or are they exceptional examples? This is something that Sung-Won Kim is going to talk about later. Here's another question. Can you realize the equality between the Nielsen number by a smooth map? This is something I spelled correctly this time. Yuzirski, he'll be talking about something a little more general than this, but this is a basic question. So the answer to this question is yes. That's right? I think maybe not. I think the answer is yes. But so Jörg is going to talk about a similar question in periodic points theory. I don't know. Boju.
This question is about periodic points.
Yes, so your talk is about periodic points. In the fixed point case,
It is yes.
it is yes. Okay.
That's Boju's paper about 1980.
Right. If you don't know who it was, you can guess Boju,
Yeah,
right?
right. That's always good.
Right. This actually, the question of smoothness is kind of a theme also, and several people have asked, you know, all the things that I've said so far today, you could ask, does it matter if you only consider smooth maps? Or is there actually a difference between smooth Nielsen theory and ordinary continuous Nielsen theory? And this is something that people have studied a lot. Does it matter? You could restrict the original map. You could require that the homotopy, all the way throughout the homotopy, is always through smooth maps. Questions like this. All right. Sometimes it does matter. Sometimes it doesn't matter. This is something that Ning is going to be talking about in her talk, I think. And I think that's all for now. So I guess I didn't tell you, my other two talks tomorrow will be about periodic points theory, and then the next one will be about coincidence points. So I hope you're not fed up with me by then. All right. Thanks.
Okay, we have some questions.